session. So I'm very pleased to welcome Jonathan Ziegler, who is working currently at Novartis in Basel, and who will speak to us about data synthesis in the medical domain. Thank you very much.
Thank you very much. Hi, everybody. It's a huge pleasure being here. I've really enjoyed the last couple of days, and it's been really nice to see this level of interaction with everybody. So I've definitely accounted for time. So please, if you have any kind of questions, just shout them out immediately, raise your hand. As soon as I see something, I'll stop talking, and we can engage in this interaction. So before I get too far into details, I'd like to tell you a little story about one of my grandmother's very best friends. Our families were really close over a long time, and I grew up knowing her kids, her grandkids. Unfortunately, the last time we met, she told me that she has been diagnosed with lung cancer. And she told me she had a chest CT done, and at that time had just started working with medical images. So I said, or I asked her if I could perhaps take a look at these images. She agreed, and while I was at her laptop, I took a few pictures. But first, let's talk about Ava a little bit more. Her full name is Ava Cook. She was born in October 21st, 1951. Her current address is 4164 Desperate Street in Atlanta, Georgia. She weighs 71 kilos, and she's 151 centimeters tall. So I told you I saw her CTs, and I thought, I'm going to an AI conference talking about medical images. Why don't I show them here? So these are a few slices of the three-dimensional volume. And while I was at her laptop, I also saw she had a brain MRI done. So I'm interested in medical images. I'm interested in data. I took a few screenshots of that as well. And these are the results. So obviously, I dearly hope that many of you have gotten increasingly uncomfortable with the fact that I'm sharing this personal information of Ava clearly without her consent. I can reassure you that's not an issue because Ava Cook does not exist. None of these things that I just said were real. Her picture was synthesized. Her demographics were synthesized. The map I showed you of her house was synthesized, and even the medical images were fully synthetic. So let's take a closer look at how this was done. For the little screenshot of her face, I used a generative adversarial model called StyleGAN 2. It was released in 2019. And if you go to the website, thispersondoesnotexist.com, you can create as many faces as you want by simply refreshing the website. An interesting fact here, though, is that it took me a very, very long time to get a woman of a certain age. I had to refresh this website quite a lot of times to not get someone in their a toddler, infant, or in the middle of their life. I was trying to get a senior citizen. I actually had to generate quite a few results before I found Ava, which I would say is senior passing, but still pretty much more towards the center of the age distribution. If you look more closely, you do also see some artifacts. The earrings are a little wonky, or for instance, is this an evil cat? Is this a person? Is this a hand? We don't really know. So there's, on the sides, there's some issues, but in general, I would say these results are fairly amazing. Another thing I would like to point out, these people are not only fairly young, they're fairly white. So this distribution always depends on what data you see at training time, and it can only represent what you're looking at unless you put some effort into it. And this is definitely something you always have to keep in mind when working with synthetic data. What was the data that was trained on? For the map, I used a very similar system. I didn't even know it existed. I just tried typing it in. This map does not exist. Worked, and I got these synthetic maps. It might have fooled you at a distance, but if you look at it closely, these models are horrible at generating text because they don't know what they see. We can see things that sort of resemble Thai. We can see something that could be Western fonts. It wouldn't pass as a real map, but for the process that I showed you, I think it worked. The demographics were even easier. I could just download a Python package and say, generate synthetic information for name, height, address for 100 people, and then it just chose the one that sort of matched what I was looking for. The medical images were taken from a publication from 2020 by Sun et al., where they showed a very interesting process for memory efficient synthesis of three-dimensional images. I'll talk about the methods in more detail later on, but the images I chose for this introduction were actually straight from their paper. So All of this was done using generative adversarial networks. We've heard quite a bit about those in the last couple of days. I will talk in more detail about those later on. If you've been active in social media and in machine learning, in the machine learning world, which I'm sure all of you are, diffusion models have become very, very popular and very, very famous. And there you can just use text prompts to generate images that you want to have. So I just went ahead and generated a few. I think I used portrait of a man with cinematic lighting, fantasy knight in shining armor, and vintage picture of an Asian city. So all of these were first shot. I didn't do any cherry picking, so these results were quite impressive. And of course, I was curious to see what presenting new ideas at a machine learning conference in Morocco would look like. Not that far away, I would say. So it's quite interesting. Yes.
How can I be sure that these pictures of people do not exist? That these people do not exist? Maybe they exist, but you don't know.
That's a very good question. For the generative models, it's fairly improbable because the generator never saw a real person. It only gets information of, is this plausible or not? So there's no gradient that passes from a real image into the generator of a generative adversarial network. For the diffusion models, I must admit I'm not that well versed, so I couldn't give you a good answer there. I will be talking a little bit more about privacy analysis towards the end of the talk, where we can look at some methods that we were using to see if we can be confident enough that this was not a real person that just kind of crept into the distribution of the synthesized data. Very good question. So let's take a bit of a closer look at the methods behind generative adversarial networks. I know we've seen talks using them, but we haven't really seen the methods behind it. I'll talk a little bit more on detail there because I am actually modifying the basic method a little bit to get these multimodal data sets. We need some kind of input noise, so a noise vector, usually normal distribution. And the reason behind that is this is our signal to the network generates something. And if we only say generate something as a ping, it'll always generate the same thing. So we need some kind of randomness to be able to actually generate a distribution of results. This noise vector gets passed to the generator. In the most popular analogy, this would be an amateur art forger in this case, that takes this noise vector as an inspiration and creates outputs, synthetic data points, fake data. This is then passed to a second neural network called the discriminator, which we can consider an amateur detective, like a art forgery detective. And it compares real data with fake data and then is tasked at deciding, is the sample it's currently looking at real or fake? And this can be computed as a loss and propagated back into the generator. A nice little piece of meta information here. I used a generative model for all the pictures in this flowchart on generative models. So I used actually Stable Diffusion to use things like Bob Ross painting a picture of trees. The thing with this model, and it kind of reflects the issues that I had with generating a picture of Ava, is we don't have direct access to what we're synthesizing. So it's more, give an example out of the distribution that you think resembles real images. And we don't really have control. We can do some exploration in the space of the noise vector, but to actually be able to condition this, we can add an additional input, which would be a condition vector. And then the discriminator is tasked not only at saying this is real or fake, but which condition or which class this belongs to. So the examples I showed you were kind of cool, I would say, but they don't really address any kind of issues in the medical world. So why would we need synthetic data in drug discovery or in a pharma company? Well, imagine you have a patient data set and you're capable of creating a model that synthesizes data points that statistically behave the same way as the original data without many of the privacy concerns that you have with the original data points. You can create something like a surrogate data set. What you can see here is actually a fully synthetic three-dimensional chest CT, and it is accompanied with clinical data, 20-some columns of clinical data, which I just showed schematic. You can use this surrogate data for quite a wide range of things. For instance, you made a breakthrough discovery, you want to share your findings, and the best way to do this would be you publish a paper, you share your code in form of a repository, and you share your data for perfect reproducibility. In the medical world, this is often completely out of the question. Imagine now you could actually publish a surrogate data set of data points that produce at least comparable results to yours based on the code with the methods that you described in the paper. This would be a huge step towards better scientific practice. Or you want to collaborate just on a fairly informal level with another university or another company. Again, if you have privacy protected data, this is very difficult. Starting off with the surrogate data set to see if the methods are sound is a very good way to lower the barrier of entry into collaboration. Using the conditional synthesis, we can also do data augmentation. So if we have a data set that is very sparse with respect to some demographics, some pre-existing conditions, we can easily fill out that area of the data set for downstream machine learning tasks, potentially improving their performance. For me, a very interesting aspect of this conditional synthesis is actually insight generation. So for that, imagine you take this synthesis model and you task it to generate a sample with condition A. And now you task it to generate the exact same sample, but with condition B. What we can do now is we can analyze the difference between these two conditions, because in theory, it's the same point in latent space except for the change of this condition. And if the network had learned enough about what defines this condition, we can perhaps actually extract some medically relevant information. And this can be an image, this can be tabular data, this can be whatever modality you're looking at. It could also be genomics data or anything else. A very, very impressive result, in my opinion, was just recently presented by Augusto Genovese's group. Here, this is one of the examples that he showed. There's a few more, but for me as a novice in the area, this was the easiest to understand. So they used thin images of thin blood smears, and they trained GAN to produce synthetic images of thin blood smears, and they conditioned on previous exposure to malaria. So some patients were exposed to malaria and they had their blood taken and some were not. And this model learned to synthesize these images. And if you can see now, we have 3 different patients which have the negative case synthesized and then the positive case synthesized. And these are exemplary for 3 different conditions that they were able to isolate. We have, for instance, these hyperchromic cells, these holes in the blood cells. We have a change of the outer structure, or sometimes it's also about coloring on the inside of the blood cells. And these, yes.
So if you go back to the previous, so what do you mean by generating exactly the same thing is that you use the same trial, the same sample from the trial?
Exactly.
So if you have 2 different conditions, you have to rely on, you have to do anything special for these 2 things to really be that related, because you have 2 different conditions A and B. It could be that neural network this time share nothing of these Z, then the trial means share no information whatsoever.
Exactly. I mean, it does require the assumption that it separates noise and condition at the input side. So that's an assumption which I can't mathematically prove, but I can tell you that the coherence in the images is fairly strong. So at least it won't have moved that far from that point in the latent space, but the conditions are sufficiently orthogonal to the noise that you can definitely produce results that are salient enough for what I'm talking about. It's penalized if it doesn't. So it's not guaranteed. It's not guaranteed that it satisfies this condition, but it's part of the loss function. Then, if it doesn't match the condition, it will be penalized. And I'll show some examples where you can see the method. This type of penalization gives you less data on the edges of categorical conditions, for instance, because it's trying to stay on the safe side and really be within this condition. So the impressive thing here, which I find really amazing, is that now we have starting points for domain experts to really look at this and analyze. These are previously unknown conditions for the exposure to malaria. Could this be something that actually holds? And could this be a new indicator to detect malaria exposition much earlier or at an easier level? So Augusto mentioned this is currently under peer review, so it's not been fully verified, but at least from the examples he showed, I find this to be a very promising avenue of research. So a lot of the medical images that I've been working with are three-dimensional, and that poses a few fundamental issues when using generative adversarial networks. So I would like to get a rough estimate from you what you think a full HD image, so 1280 times 720 pixels, 24-bit color, what that would require in memory, one single color image. Does anyone know off the top of their head? Okay, show of hands, who thinks it's less than 50 kilobytes? Who thinks it's less than 1 megabyte? Who thinks it's less than 5 megabytes? Very good. It's 3 megabytes approximately. So this is we've seen models be able to train on very, very complex, deep structures, convolutional neural networks with this type of input. But for a three-dimensional medical image, for instance, a brain MRI, 192, or say 256 by 256 by 256, and we're then at 32-bit resolution. Who thinks we're still under 5 megabytes? Pardon? You'd say it's more. So do you think it's under 50 megabytes? Yes? 60? 16? Well, I changed the resolution. I cheated a little bit. So this was 24-bit. I was working with 32-bit. So then we're actually at 70 megabytes. I mean, and this is just a fairly small image. For instance, for a CT, say 400 by 400 by 1400, we're almost in the gigabyte scale. And you'd think, okay, well, my GPU has 32 gigabytes, no problem. Batch says 32 or 16, and we're fine. Well, we have gradients, we have intermediate steps that have to be saved. So this is immediately a huge issue when trying to train neural networks. The memory requirements become very complex. So the initial thought was, well, we can train something smaller and then upsample and everything will be just fine. These are some initial results from that thought. We used a vanilla DCGAN, added a dimension, 64 cubed, upsampled. And I think you would agree, these are not great. I mean, these were absolutely ridiculous. Supposedly, this is a lung cut through this axis and the frontal view. With some imagination, you can see the heart and the two lungs, but nobody would believe that this is a real scan. So going back to the neural network architecture of the GAN that I showed earlier, we modified that in a certain way. So here we're now using, again, noise input and a generator, but this does not produce our output. This produces a four-dimensional hypercube, which is just an abstract activation. And this then passes through two different branches. The first is a high-resolution sub-volume generator. So this, we take the hypercube, take a few slices out of this, and pass it into this generator. So instead of getting a noise vector, this gets a few slices of the hypervolume. And it is tasked at producing a few slices of high-resolution images. So 256 by 256 by 32 slices in our case. And this is then paired with the associate discriminator. And this generator is very good at local details. It can produce very nice resolution, local details. It can give us a lot of information, but it doesn't have any information on the global structure of what we would consider, for instance, the lung or the brain. This is taken by the low resolution generator. Here we take the full and produce a low resolution, full three-dimensional volume of 64 by 64 by 64 voxels, and pair that with the associated discriminator again. The only thing we have to do then is to modify the training data in a way that matches the modality that the discriminators are looking at. So just a few slices of high resolution data or downsampled volumes for the low resolution generation.
Already at the top one, when you were generating 8 slices, did you have to do anything special so that these 8 slices were consistent with each other?
No, this is a fully three-dimensional architecture, so it'll maintain the consistency over the 8 slices. This last step. Pardon? That's a good question, because right now all we have is either a few slices of high-resolution data or a low-resolution volume, and we've gained absolutely nothing. But I'll come to that in just a few seconds. The advantage during training here is that not once do we actually propagate a full three-dimensional volume through this network. There's no backpropagation of a full three-dimensional volume. So the memory constraints are a lot more relaxed, and we can actually train this model. But we are maintaining, or we are enforcing both global structures and local details within the activation generator, because the gradient propagates all the way into that component of the network. So in other words, this component, although it doesn't actually output something that makes sense to us, in theory, it has to have the modeling complexity to produce all the information we need for both branches. When it comes to inference, you're right, we haven't really solved the problem of synthesizing full three-dimensional volumes. For that, luckily, we can remove many of the components of the network. Backpropagation is not an issue anymore. So this is what the final synthesis model looks like. We only have the activation generator and the high-resolution generator. And note, we remove the subvolume sampling. So this gets the full hypercube, and as it's a convolutional architecture, it can immediately produce the full three-dimensional volume without stitching multiple instance inference and things like that. This directly end-to-end synthesizes our three-dimensional volumes, which is a huge advantage, because we don't get any kind of issues with boundaries or discontinuities this way. The initial examples that we got from this from this model were actually quite good. First glance, there's a reason I'm showing them in such small thumbnails, but the first impression was quite positive. What you see here is always a triplet of the three main axes of the image. And so many of these do represent a lung, and we can definitely see details. We can interpret things like vertebrae units here. But there are a few issues. Some of these images definitely don't make sense. So looking at those failure cases, we can see there's strong artifacts. There's some that I would consider complete nonsense, where I wouldn't be able to interpret those. And another thing we noticed, you get these bars in many of the images, which come from padding in the training data. So the synthesis model thinks that padding with zeros is a very good idea to turn this into a plausible image. Another thing we looked at there was conditional synthesis. So conditioning our images on the body mass index. This is not exactly a very exciting condition, but it's a condition that we can quickly visually verify. Does this person look skinny or not so skinny? And these are a few examples. Here again, we have the center slice in this axis for 8 individuals, and I modified the BMI from top to bottom. And so as you can see, some of these make sense. And but I'd like to point out what we see in the low BMI category. If you think about a BMI, low BMI, skinniness can be considered not a lot of pixels in the scan volume are occupied by the human being. Another thing that doesn't occupy a lot of volume in the scan is the head. So the neural network decided scans of heads and necks are definitely more probable to be low BMI. And it also produces, for instance, noses on chests. So it's kind of trying to turn this characteristic of headness into a low BMI condition. So that was a really clear pointer for us that we had to look at the data. So set the model aside for a while and started really manicuring the data a little bit. And at this point, the data set, it's an internal data set. It was around 2,500 patients, resulting in, I think it was 300 terabytes of images. The way I did this now was actually to try to produce isotropic 256 cube volumes centered around the lung. And I must say, I was very impressed at how easy and quick this was possible to do with existing repositories, methods, and libraries that are currently available. So I think this has really advanced to a point where someone like me who doesn't want to write a master's thesis about it or spend weeks developing a new model can actually download something and make it work in time frame of a day or maybe 2 days. And so the way this worked is I used the model called lung mask. You can just download the repository if you want. Fed these 3-dimensional CT volumes in and check if enough lung volume was present in the scan for me to consider it a lung scan. So if it was a head and neck scan or a pelvic scan, I disregarded this image. If we had enough information, I drew a bounding box around the segmentation map, saved the image to a new file, saved the segmentation map, and the bounding boxes for later use. But this was a process I had to do once. It took a couple of days to run, but now the entire data set was nicely prepared. I removed around 50% of the data, but the performance increased noticeably. So these were the results with the exact same model trained on the smaller but higher quality data set. As you can see, it's much more confident in the contrast. So the densities make more sense, less artifacts, and no failure cases. So that was a very, well, in my visual inspection, I didn't find any failure cases. I don't want to claim that this model has no failure cases, but at least considerably less. So before I pivot to clinical data synthesis, are there still some open questions about this part right now?
How do you know that this is like an IIT sample where I guess like conditional BMI? So did you run like a test where you took your 2,000 samples and then ran a classifier that said like given this image what the BMI is and then compare the synthetic data with the actual data?
Yes, I'll show a few of those analyses a bit further down the road when we're looking at the multimodal data. But yes, we analyzed the whole data set also on the statistics to make sure that it makes sense.
So on the earlier slides, you showed that you could say that for the generated samples of yes and on the whole part of the dimensional behind that. Gray and one of the blacks.
That was the rationale of cropping down the data set then. So the space of possible images was much larger than what we intended. And by reducing the amount of data available to really only look at chest CTs, this made things just increase the quality of the images greatly.
So then you can start to play with BMI on it.
Yes. We'll look at that later on as well. The bounding boxes were achieved by just looking at the maximum dimension of the segmentation map in all three dimensions. And then we had the bounding box. No, I used a three-dimensional ResNet for the segmentation. And so then we get this, what you see in the red and blue colors, which is a three-dimensional segmentation map. We have 0, 1, and -1 for the three classes, left lung, right lung, no lung. And that we could then use to estimate the segmentation map. And for our task, the actual quality of the network wasn't even that relevant because I really don't care how well it segments in the inside. It's just about the outermost pixel in all three dimensions for this application. All right, so the next task was synthesizing structured data, tables of data. And for that, there's very good tooling available. There's no need to necessarily reinvent the wheel at every step. So I started with the Synthetic Data Vault Toolkit, which gives us decent methods for sampling from distributions. It gives us GAN-based methods as well. And it has a full suite of tools on benchmarking and evaluation. For the benchmarking and evaluation, or mainly for the evaluation side, there's a few different things you can look at. One is, how do the distributions match? Do the individual univariate distributions of the synthetic data match that of the real data? Then you can look at how well do models perform trained on the real data set versus trained on the synthetic data set. And then the last is to use an adversarial attack. Can I train a model that can detect the difference between the synthetic data set and the real data set? So I took this tooling and I just naively synthesized 24 columns of medical data. I gave the model no information about the data types, no information about the distributions. I really just fed this in. And the results were actually quite decent, both for continuous columns and also for discrete columns. These were free text as well at some point. And you can see it's not a one-to-one match, which I'd be afraid of. So if the distributions would match completely, I would expect some kind of information leakage. But at this point, I would consider this a decent first glance performance. A more interesting aspect to analyze is actually the multivariate correlations. So can the model capture multivariate dependencies in our data? Here you can see the real data set, the synthetic data set, and the difference signal. I'd like to point out these two big errors in the center. These were actually a type of quality control that I left in my data set intentionally. There are two columns that are 100% correlated, one in free text and the other as a binary value. And the model undercommitted on this 100% correlation. But other than that, we had, for privacy reasons, I can't really show you the categories, what the clinical values were, but we have things related to demographics. We have things related to pre-existing conditions down here. For instance, height, weight, and BMI, there's a correlation there. And so that, it picks it up quite nicely. So now the big question is, how can we take these multiple modalities and turn them into a multimodal model? And for that, I use the shared latent space synthesis. So we already saw some examples of that with our image generator, because we have our shared generator, our noise, our condition, and this gets passed into the two branches. This is essentially the same picture that we saw earlier, just with blocks instead of pictures. And nothing's stopping us from adding something more to dock on another modality head onto the shared latent generator. And in this case, we use it for structured data. The difference here is, though, that humanly readable structured data and what the GAN sees underneath is very different. So we have to add a certain amount of transformation, inverse transformation around this machine understandable GAN to make it work. But in concept, it was pretty simple to just connect the activation into the generator of this GAN and then produce a multimodal output. The nice thing here is that as we have the connection between local structures and global structures and local details in the image, we also encourage cross-modal correlation by using this shared generator. So things we see in the image should hopefully appear in the tabular data. It's not enforced, but it is encouraged. So let's go back to the conditional synthesis on BMI that we looked at earlier. Here we have some of the results from the multimodal model. Again, we have our 8 patients, we have the center slice vertical axis, and the BMI is increased from top to bottom. You can see that the coherence in the image from condition to condition is fairly decent. And if we look at the difference signal, it does what we would expect. It increases tissue volume for a higher BMI. The statistical analysis here we did with just distributions. We gave it a clear cutoff of densities. That's the nice thing with CTs. The values actually mean something. So we were able to just do a density cutoff for everything except for air and bone. And we looked at the BMI distribution by just the percentage of scan volume occupied by the patient. This is not 100% accurate, obviously, because in the real images, we still have certain distribution of the location of the patient. But as you can see, at least it does match the trend over the 4 categories. And you can also see something that I mentioned earlier. The synthetic model prefers to stay away from the edges of these categories, although it is actually a continuum. So trying to model on more categories or add some additional tooling there to prevent this might be a good thing to have. So obviously, BMI, as I mentioned, is not super exciting, but it is a good starting point. We did look at conditioning on more complex multivariate conditions. For instance, the progression-free survival for 1 year. What that means is, does a person have a progression of the sickness that we're investigating within 365 days of the baseline visit? Again, we have our 8 patients, center slice. Please keep in mind that for every picture that you see here, there's always a full clinical data set, a full clinical set of information accompanying this. I'm just showing the images because they're much easier to interpret. The top row is the positive case. So these synthetic patients had at least 1 year of progression-free survival. And the center is the negative case. So these people had a progression, or these synthetic people were considered to have had a progression within the next 365 days. And what you can see here is the model produces at least fairly homogeneous changes. It seems to have an idea of what the difference might be, which is a reduction in lung volume, a reduction in heart volume, and a reduction in tissue volume. This is far from an insight. This is just what a model thinks this could be. This is still pre-verification from domain experts, from medical professionals. So do take this with a grain of salt. This is just a trend that I have witnessed, and I would think it would be interesting to investigate. I mean, often these things are also correlated with comorbidities. If you're sick, you might be laying in bed a lot. If you're laying in bed a lot, you might lose weight, things like that. So it doesn't necessarily have to be directly connected with the sickness you're looking at, but it is definitely a starting point. Another way to investigate the quality of the synthetic data, so not necessarily from the conditioning perspective, but in general, how good is the synthetic data set? How well can we use it for our variety of tasks? Is to look at the distribution of, for instance, latent representations of these images. So I made use of a existing pre-trained three-dimensional classification network. No, this was a organ segmentation network, but actually I just grabbed the pre-trained ResNet 50 backbone out of this network. It was trained on a very wide variety of organs, tasks, and image modalities. But I was really just interested in this part. So what this does, it takes an MRI or a CT or whatever we're using, and it embeds it into a vector of dimension 2048, and we can use that to visualize. So I then just did dimensionality reduction. I took a UMAP, and we could look at the clusters. So I'd like to start with a negative example from pretty early on in the process for you to understand what you hope not to see. So we have two data sets in blue and orange, and then we have three different synthesis models in purple, red, and in green. And the purple and the red, you can see, produce plausible results. They're well within the distribution of the real data, but they do not cover a very large area of space of the real data. So this would be, I would consider a mode collapse. It only produces a very, very small subset. Problem is, if this subset is in the hundreds, you might not actually see it if you're doing visual representation. If you're just looking at the images, you might not notice that these are from a very small distribution. When clustering, this becomes very apparent. These images might have high fidelity, but they have very low diversity. And for the green synthetic data set, we have some clear outliers. For instance, here, these we probably have some kind of artifacts, have nonsense. And so there we could say that the fidelity of the data is not as high as we might have hoped. Next, I would like to look at some of the clusters of the data that we looked at just before. So this was the multimodal synthetic data set on conditioned on BMI. On the right-hand side, we see the image embeddings. On the left-hand side, we see the direct reduced visualization of the clinical data. And here we can see it's a bit dense, but we can definitely see that the synthetic data points overlap quite well with the real data points, and it covers the entire space. So even what you would think might be outliers, there's actually real and synthetic data points at all of those. So the diversity is quite high, and the fidelity is also quite high because we don't have massive outliers of synthetic data points. And an additional thing that you can see here is that sorry, yeah. Sure. No, it's UMAP axis 1, UMAP axis 2. So it's just the no meaning. Right. So the labels also match. So the conditioning, although we saw it already in the distribution, there's a bit of smearing at the borders. We do have an overlap that the categorization of our images, so the conditioning seems to be working quite well. Similar situation here on the left with the clinical data. It's a little more difficult to analyze just because there's a bit of movement going on here, but all in all, I was quite happy with the results of this. Next, I would like to go a little bit more into privacy, because that was my selling point at the beginning. It's like, hey, we can share data, so this better be private. Yeah.
Can you go back to the violent topic? couple of slides ago.
Absolutely.
Oh yeah, here now. So in this case, as I'm reading it, the purple, I guess like your range, I guess like below BMI is, I don't know, 0.33 to 0.6. Whereas for the synthetic data, it's like 0.33 to 0.42. I guess like the undersampling of the range, that seems problematic, but is it?
I think it really depends on what you want to use the data for. I have kind of gotten to a point where I maybe have developed a certain tolerance to that kind of issues in medical images because the reported values are so noisy. So I wouldn't necessarily trust every BMI or every weight that somebody's reported. So this was, this is a clinician noted this down. So there's a fair amount of noise in that. Plus, this might be just because of weight distribution. Some people, have a lot of their body mass in the lower half. And so I was only looking at the chest. So this is also a certain level of uncertainty with what we're seeing versus what's on paper is definitely an issue here as well.
So in this case, how you've calculated the percentage of tissue for both real and
they're identical.
So they're identical.
Yeah.
So then you could, I guess, aggregate this, but it still seems like the top of the range is understandable.
It is. And it's an interesting fact that I haven't really been able to explain. So at that point, I was pretty happy that the trend matched, but the fact that this undersampling occurs is still an issue where I'm not quite sure if it's just a density cutoff issue, so that maybe the model isn't as confident in producing high density or zero. Well, zero less because the bottom seems to be matching quite well. But that's definitely something that I'm still struggling with understanding for sure. Yeah. Let's see here. We were here. So talking about privacy. This is actually from the work of a few of my colleagues. And what they did was they synthesized vertebrate units. So these were just individual vertebrates. Looks like it's a little difficult to see the picture here. You might just have to read the paper. I'll share you the title of that in just a second. But essentially what we can see is for 3 different categories, which is just the location of the vertebra. They produce synthetic images. Similar method at visualizing the distribution of the data set. It's a bit noisier, but you can see that it's, at least in terms of the quality, is not complete nonsense, but their focus was actually analyzing privacy. And this is a post-hoc way to look at privacy. So this is not formalized. This is more looking at a synthetic data set and making sure it is impossible to very hard to re-identify individuals from the training data. And they used 2 different methods for that. One was the pairwise attack and one was the distribution attack. So for the pairwise attack, you can think of if you have a few samples and you want to see which one of these might have been part of the training data, you just compare the synthetic output with your candidates. And if you have an example, for instance, this 4, that matches perfectly, chances are pretty high that this was an example that was in the training data set of your model. If you have sort of some overlap, but not a perfect match, maybe it was, but most likely it wasn't. And for the 0, for instance, we don't have any elements of this category at all. Either our model is performing very badly, or this was never part of the training. And for the distribution, we can look at how many examples of a certain similarity occur in the data set. So here we can see there's no 2s, no 0s, but a lot of 1s. So most likely this was trained on 1s. So these 2 methods were both used to analyze this data set. Here you can see the distribution of synthetic data over the real data points. And although this is a nice visualization, I prefer looking at the projections here, and you can actually see that the distributions are fairly similar. So we don't have massive clusters of synthetic data points around individual real data points. Agreed, with strong oversampling, this could become more apparent, but at this point, we could consider this, at least from a distribution perspective, to be fairly privacy conserving. The distance metrics, they didn't have a good visualization, but it is definitely the case that they weren't able to to perform any kind of pairwise attacks. So there was no single images that they could identify from the training data set. And in terms of efficacy, they trained two different models, the same models on synthetic and real data for just classification of which area this vertebra unit comes from. And they both perform quite similarly. So for more details, feel free to check out this publication. It's definitely an interesting one to look at. I personally did some more investigation into the clinical data side of things. So not images, but looking at the clinical data. This was vetting a few different vendors that were trying to sell synthetic clinical data. And here we can look at the smallest nearest neighbor distance. So this is the distribution of every real point compared to every synthetic data point. And for the two vendors, you can see they must have used very different methods because the results are very, very different. One of them has a sharp peak close to a zero distance, and the others have a strong distribution. And for both of these vendors, we can see it's not mainly a zero distance. If you'd see this, some alarm bells should go off because we have a few exact hits, but this was due to the fact that I only used a subset of the columns. When I used all the columns, so I expanded the dimensionality of the space, we had no exact hits. So in terms of privacy, we could be fairly confident. But looking at the distribution again, there's some serious issues because the real data is not represented well by either of the vendors. We have a lack of diversity and strong outliers by one of the vendors. So a lack of fidelity as well. Both of these factors did play into the evaluation of the quality of the data. And I would say, yes, they're private, but we know they're not very good. This is a trade-off you have to consider. So if privacy is your main concern, this might be something you can share for pipeline development. You just want to make sure your code runs, your visualizations run, and the pipeline works, then this is a great thing because it feels like real data, but it won't behave the same way. But if you're actually trying to reproduce results or do any kind of collaboration on that, this will not be the level of quality that you need. So what's the current status? Internally, this multimodal conditional GAN is packaged, documented, and is currently being beta tested in other use cases. I created a fully synthetic data set with 10,000 synthetic patients, full three-dimensional images, accompanied with clinical data. So any associate that wants to experiment with this can just access the synthetic data set without having to go through all the rigors of the accessing the trial data. And the models are available, so if they want to produce a different distribution of the conditions, this is also no problem. I'm pretty excited about various aspects of further steps. So one would be to formalize privacy. What does privacy mean with respect to different modalities, and how can we introduce this at training time? So can we formalize privacy laws? Can we introduce elements into the network that enforce a certain privacy, such as Gaussian privacy networks? Another thing is progression modeling. So we were only looking at one point in time at this. I mentioned memory issues, so just adding another dimension, the time dimension, is not an option. You have to find ways to build decent longitudinal models, or as a starting point, just condition on time point. That would be one way to look at it. And lastly, new modality hits. So we could look at genomics. I did a few initial experiments on genomics, but if you don't know enough about the subject matter, this is a very tough one to crack. You can also do free text, doctor's reports, MRIs, X-rays, you name it. So the option for new modalities, as long as you have the data sets for training, are pretty open. To summarize, synthetic data can solve existing challenges in R&D for drug development and within clinical trial design. The method that we have synthesizes full-scale three-dimensional images and clinical data, but can be expanded to other modalities. And the data quality at this point is good enough for practical use with some applications. If you want to read more about it, this was published, I think, 2 weeks ago at a NeurIPS workshop. And if you're interested in interacting more, definitely feel free to reach out. I'll leave the slide open for just a second. A few phones popping up. If you want to reach out, contact any one of us. Feel free to. Maybe you're interested in trying out the methods. We hope to open source the entire code within the next quarter. With that, thank you very much for listening. I'm very curious to hear if you have any kind of
a few questions.
I had a question about privacy.
Yeah.
So I think privacy is something that you use your own definition, but I think from country to country, it might be a completely different thing.
Yes.
And it's going to be defined by lawyers, not by people who do machine learning. So how easily do you think that we can adapt to different laws in different countries? And I think some countries might at some point decide that privacy means that also means that you're not allowed to use data that belongs to somebody. I mean, I wouldn't be surprised if these supposed to go at some point.
Yeah. So it's not only between country and country, it's also individual companies or vendors of privacy preserving methods have their own definition. So this is something I think as a community, we have to formalize and really structure in a way that makes sense. And from a perspective of the lawyer's vision of things, I think this is a very tricky one. So I intentionally trained on de-identify. So this was already private data before I started. So even if an individual would retract their consent to use this data, this is not a problem. This is fully anonymized data as it is. But this step is definitely one that is very relevant, because if we can't pass that issue, it won't have any use. Absolutely.
How much do you care about, I guess, with your synthetic data, like sample quality versus sample diversity? Because right, different model classes kind of have different trade-offs on that aspect. GANs kind of really trade off, sample diversity for sample quality, kind of DAs, but almost vice versa.
I would say that really depends on the use case. For it, you can enforce greater diversity in the GANs by adding an autoencoder branch to really force the model to be able to reproduce every element that was available in the training data. But I would really say it depends on what you want to do.
First of all, I would like to congratulate you for all what you've done in your research team. Your MRI looks really real. My question will be taken from another standpoint, mostly the clinical standpoint, because, well, from our own experience in my research organization, we've been working on generating synthetic medical images for years. Always the one and unique problem was the resistance from the medical community. I'm very glad to have more people doing this militant campaign for this cause. My question will be split into two parts. First, I would like to know either you have any domain experts with you within this process for the validation, the analysis, and all what you need to do from the clinical files with your images. Second, either you reach to deploy all these images within some computer assisted diagnostic systems within real clinical routines and hospitals, or not. Thank you.
So during the process of selecting salient covariates from the clinical side, we had trial statisticians assist us with that. So that I didn't, because my domain knowledge is minimal in that aspect, so that I didn't choose complete nonsense columns that wouldn't be indicative of anything. So they helped us choose the right ones. And I had regularly people look at the data, and I think it's still, at this point, still somewhere in the uncanny valley that people look at it and they're like, wait, this doesn't quite match, and they lose trust quite quickly. So that's depending on what you want to use it for, this can be an issue. For instance, if we had one situation where it was just about building a demonstrator for some tooling, but then people with domain knowledge were starting to realize that there's some correlations weren't popping up the way they wanted to. And they were immediately, no, we have to use real data for that. So yes, there's still some work that has to go into fine-tuning which elements really have to be correct. And perhaps we can also introduce, which just is more work, but it's easily doable, introduce boundary conditions that enforce some of these correlations. And for your second question, at this point, we don't really plan to deploy this at hospitals. This is more for research internally or for collaboration externally, but not through the hospitals.
Now there is more promising, let's say, market out there for let's say new research and reach hospitals and networks. I don't know if you are familiar with cycle-consistent generative adversarial networks. That can be not made only for generators, but also for some data distribution normalization, the follow staining normalization in pathologies like cancer, hematoxin, and AOD. All these can, I see it from my perspective, is a very promising research line that could lead you to explore real different.
I was actually also looking at this method for batch effect correction. So correcting for different scanner types with MRIs, for instance, this can be slight modifications. You have to be able to actually encode real images into the noise space. But other than that, yeah, it's definitely an interesting, different avenue, but very interesting to explore.
And the internal, the validation is done by your data from your internal organism, your own data, right?
Yes. At this point, yes, but I mentioned we're open sourcing, and for that we'll be using a public data set, so you can reproduce everything. Thank you.
Maybe a last question. Okay, so merci beaucoup. Thank you very much.
Thank you.
So we will move to the second speaker.